Welcome to Chemistry Half-Life Calculations. Half-life is one of the most intuitive and practical concepts in chemical kinetics. It tells us how long it takes for the concentration of a reactant to drop to 1/2 of its initial value. But here is the fascinating part. The half-life depends on the reaction order in a unique way. For zero-order reactions, half-life is proportional to the initial concentration. For first-order reactions, half-life is constant, completely independent of how much reactant you start with. For second-order reactions, half-life is inversely proportional to the initial concentration. In this presentation, we derive the half-life formula for each order, work through 5 quiz questions and 5 detailed problem solutions, explore real-world applications like radiocarbon dating and drug metabolism, and consolidate everything in a comprehensive summary. The half-life, denoted T1/2, is the time required for the concentration of a reactant to decrease to exactly 1/2 of its initial value. After one half-life, concentration A equals A0 over 2. After 2 half-lives, A equals A0 over 4. After n half-lives, A equals A0 divided by 2 to the power n. This exponential relationship makes half-life such a powerful and intuitive concept. You can quickly estimate how much reactant remains without doing any exponential math. But crucially, the way half-life behaves depends on the reaction order. For first-order reactions, half-life is a constant. It does not matter whether you start with 1 molar or 0.001 molar, the time to reach half that concentration is the same. For zero-order reactions, each successive half-life is shorter because there is less reactant to consume. For second-order reactions, each successive half-life is longer. Understanding this difference is key to identifying reaction order from kinetic data. To derive the half-life expression for any reaction order, we start with the integrated rate law and substitute concentration A equals A0 over 2 when time equals T1/2. For zero order, A0 over 2 equals A0 minus K T1/2, giving T1/2 equals A0 over 2K. For first order, ln of A0 over 2 equals ln A0 minus K T1/2, which simplifies to ln of 1/2 equals negative K T1/2. So T1/2 equals ln 2 over K, which is 0.693 over K. Notice that A0 cancels out completely. This is why first-order half-life is independent of initial concentration. For second order, 1 over A0 over 2 equals 1 over A0 plus KT1/2, giving 2 over A0 minus 1 over A0 equals KT1/2. So T1/2 equals 1 over K times A0. Each derivation is straightforward once you have the integrated rate law. For a zero-order reaction, the rate is constant and independent of concentration. The integrated rate law is A at time t equals A0 minus KT. Substituting A equals A0 over 2 at t equals T1/2 gives A0 over 2 equals A0 minus K T1/2. Solving gives T1/2 equals A0 over 2K. The half-life is directly proportional to the initial concentration, double A0, and you double the half-life. After each successive half-life, the concentration drops by half. But since the rate remains constant, the time needed to consume each subsequent half decreases. The second half-life is A0 over 4K, half of the first. Zero-order kinetics occur in saturated enzyme reactions, photochemical reactions, and decomposition on catalytic surfaces. The constant rate means the reactant is consumed linearly with time until depletion. First-order half-life is the most elegant and practically useful case. Starting from the integrated first-order law, ln A at time t equals ln A0 minus KT, substitute A equals A0 over 2. ln of A0 over 2 equals ln A0 minus K T1/2. This simplifies to ln of 1/2 equals negative K T1/2. So negative ln 2 equals negative K T1/2, giving T1/2 equals ln 2 over K equals 0.693 over K. The initial concentration A0 cancels out completely. The half-life depends only on the rate constant K. This constancy is the defining feature of first-order kinetics and the reason why half-life is such a powerful concept. After each half-life, exactly half of the remaining reactant decays, regardless of how much is left. This exponential decay behavior is observed in radioactive decay, drug metabolism in the body, many isomerization reactions, and the decomposition of many pharmaceuticals. For second-order reactions, the story is very different. Using the integrated law 1 over A at time t equals 1 over A0 plus KT, substitute A equals A0 over 2. 1 over A0 over 2 equals 1 over A0 plus KT 1/2. This gives 2 over A0 minus 1 over A0 equals KT 1/2, so 1 over A0 equals KT 1/2, and T 1/2 equals 1 over K times A0. The half-life is inversely proportional to the initial concentration. Double A0 and the half-life is cut in half. This means that as the reaction proceeds and concentration drops, the half-life gets progressively longer. The second half-life is twice as long as the first, the third half-life is 3 times as long, and so on. This characteristic makes second-order reactions easy to identify experimentally. If you measure half-life at different initial concentrations and find that T 1/2 times A0 is constant, you are dealing with a second-order reaction. The stark contrast in half-life behavior across reaction orders provides one of the most reliable experimental methods for determining reaction order. Zero order, T 1/2 is proportional to A0. First order, T 1/2 is constant, independent of A0. Second order, T 1/2 is inversely proportional to A0. If you perform an experiment at 2 different initial concentrations and measure the half-life, the pattern immediately tells you the order. For zero order, doubling A0 doubles T 1/2. For first order, T 1/2 stays the same. For second order, doubling A0 halves T 1/2. This diagnostic tool is simple, visual, and requires no complicated mathematics. Just measure the time to reach half the initial concentration at 2 or more starting points. The half-life method complements the graphical method and provides a quick check of your results. Half-life has enormous practical significance across multiple fields. In nuclear chemistry, the half-lives of radioactive isotopes range from fractions of a second to billions of years. Carbon-14 dating uses the constant half-life of carbon-14, 5,730 years, to determine the age of archaeological artifacts. In pharmacology, drug half-life determines dosing schedules. A drug with a 6-hour half-life needs to be taken every 6 to 8 hours to maintain therapeutic levels. In environmental science, the half-life of pollutants tells us how long they persist in the ecosystem. In nuclear medicine, isotopes used for imaging must have half-lives long enough to perform the scan, but short enough to minimize patient radiation exposure. Technetium-99 meters with a 6-hour half-life is ideal. The universal principle. First-order half-life is constant. Zero and second-order half-lives change with concentration. Understanding which regime applies is essential for accurate predictions in all these applications. Quiz question 1. For which reaction order is the half-life constant, independent of the initial concentration? Option A, zero order. Option B, first order. Option C, second order. Option D, all orders. Take a moment to think about this. The correct answer is B, first order. Only first-order reactions have a constant half-life that is independent of the initial concentration. First-order T 1/2 equals ln2 over K, which is 0.693 over K. There is no A0 term. For zero order, T 1/2 equals A0 over 2K, which is proportional to A0. For second order, T 1/2 equals 1 over K times A0, which is inversely proportional to A0. Quiz question 2. If the initial concentration of a zero-order reaction is tripled, what happens to the half-life? Option A, it is divided by 3. Option B, it stays the same. Option C, it triples. Option D, it increases by a factor of 9. The correct answer is C, it triples. For zero order, T1/2 equals A0 over 2K. Tripling A0 gives T1/2 prime equals 3 times A0 over 2K, which is 3 times the original T1/2. The half-life triples because it is directly proportional to the initial concentration. Quiz question 3. A first-order reaction has a half-life of 40 seconds. How long will it take for 90% of the reactant to be consumed? Option A, 80 seconds. Option B, 120 seconds. Option C, 133 seconds. Option D, 160 seconds. The correct answer is C, 133 seconds. If 90% is consumed, 10% remains. Use the formula A over A0 equals e to the negative kt. Since k equals 0.693 over T1/2 equals 0.0173 per second, then ln of 0.10 equals negative 0.0173 t, so t equals 133 seconds. After 3 half-lives, only 12.5% remains. After 3.32 half-lives, 10% remains. Quiz question 4. A second-order reaction with K equals 0.040 per molar per second has an initial concentration of 0.50 molar. What is the half-life? Option A, 25 seconds. Option B, 50 seconds. Option C, 75 seconds. Option D, 100 seconds. The correct answer is B, 50 seconds. For a second-order reaction, T1/2 equals 1 over K times A0, which equals 1 over 0.040 times 0.50, giving 1 over 0.020 equals 50 seconds. If A0 were doubled to 1.00 molar, the half-life would be 25 seconds, half as long, showing the inverse relationship. Quiz question 5. An experiment measures these half-lives at different initial concentrations. At 0.80 molar, T1/2 is 62.5 seconds. At 0.40 molar, T1/2 is 125 seconds. At 0.20 molar, T1/2 is 250 seconds. What is the reaction order? Option A, zero order. Option B, first order. Option C, second order. Option D, cannot be determined. The correct answer is C, second order. As A0 decreases, the half-life increases. When A0 is halved from 0.80 to 0.40, T1/2 doubles from 62.5 to 125 seconds. This inverse proportionality, T1/2 proportional to 1 over A0, is the defining characteristic of a second-order reaction. Problem 1. First-order half-life calculation. A first-order reaction has K equals 0.0462 per second, with initial concentration 0.500 molar. Calculate the half-life, the time for 90% decomposition, and the fraction remaining after 60 seconds. Step 1. Calculate the half-life using first-order formula. T1/2 equals ln2 over K. Using 0.693 divided by 0.0462, we get exactly 15.0 seconds. Step 2. For 90% decomposition, 10% remains. Using ln of A over A0 equals negative KT, we have ln of 0.10 equals negative 0.0462 T. Solving, T equals 2.303 divided by 0.0462, giving 49.8 seconds. Step 3. Check using half-lives. 49.8 divided by 15 equals exactly 3.32 half-lives. 1/2 to the power 3.32 equals 0.10, confirming 10% remaining. Step 4. Calculate fraction remaining after 60 seconds. A over A0 equals e to the negative 0.0462 times 60, which equals e to the negative 2.772, giving 0.0625. That is 6.25%. As a check, 60 seconds divided by 15 seconds per half-life is 4 half-lives, and 1/2 to the fourth is 1/16 equals 0.0625. The answer, half-life is 15 seconds, time for 90% decomposition is 49.8 seconds, and after 60 seconds, 6.25% remains. Problem 2. Zero-order half-life calculation. A zero-order reaction has initial concentration 0.600 molar and K equals 0.012 molar per second. Calculate the half-life, concentration after 20 seconds, time for complete consumption, and the second half-life. Step 1. Calculate the first half-life. For zero order, T1/2 equals A0 over 2K. That is 0.600 divided by 2 times 0.012, which equals 0.600 divided by 0.024, giving 25 seconds. Step 2. Concentration after 20 seconds using the integrated law. A at time t equals A0 minus KT. So A at 20 seconds equals 0.600 minus 0.012 times 20, which is 0.600 minus 0.240, giving 0.360 molar. Step 3. Time for complete consumption. Setting A equals 0. 0 equals 0.600 minus 0.012 T. Solving, T equals 0.600 divided by 0.012, giving 50 seconds. Complete consumption takes exactly twice the first half-life. Step 4. Calculate the second half-life. After 25 seconds, concentration has fallen to 0.300 molar. The second half-life equals 0.300 over 2 times 0.012, which equals 12.5 seconds. Notice the second half-life is half as long as the first, demonstrating that zero-order half-lives decrease as concentration drops. Answers: half-life 25 seconds, concentration after 20 seconds is 0.360 molar, time for complete consumption 50 seconds, second half-life 12.5 seconds. Problem 3. Second-order half-life calculation. A second-order reaction has K equals 0.0350 per molar per second, with A0 equals 0.400 molar. Calculate the half-life, concentration after 75 seconds, time to reach 0.100 molar, and the second half-life. Step 1. Calculate the first half-life. For second order, T1/2 equals 1 over K times A0. That is 1 over 0.0350 times 0.400, which equals 1 over 0.0140, giving 71.4 seconds. Step 2. Concentration after 75 seconds. Using 1 over A at time t equals 1 over A0 plus K. T 1 over A at 75 equals 1 over 0.400 plus 0.0350 times 75. That is 2.50 plus 2.625 equals 5.125 per molar. So A at 75 equals 1 over 5.125, which is 0.195 molar, very close to a half-life value. Step 3. Time for A to drop from 0.400 to 0.100 molar. 1 over 0.100 equals 1 over 0.400 plus 0.0350 T. 10.0 equals 2.50 plus 0.0350 T. So 7.50 equals 0.0350 T, giving T equals 214 seconds. Step 4. Calculate the second half-life. After one half-life, concentration is 0.200 molar. Second half-life equals 1 over 0.0350 times 0.200, which equals 1 over 0.00700, giving 143 seconds. The second half-life is twice as long as the first, exactly the expected behavior for second-order kinetics. Answers: half-life 71.4 seconds. Concentration after 75 seconds is 0.195 molar. Time to reach 0.1 molar is 214 seconds. Second half-life 143 seconds. Problem 4. Determining order from half-life data. Kinetic data at different initial concentrations. At 0.50 molar, T1/2 is 24 seconds. At 1.00 molar, T1/2 is 12 seconds. At 2.00 molar, T1/2 is 6 seconds. Determine the reaction order and calculate K. Step 1. Test the zero-order hypothesis. For zero order, T1/2 is proportional to A0. From 0.50 to 1.00 molar, A0 doubles, but T1/2 goes from 24 to 12. It halves instead of doubling. Zero order is ruled out. Step 2. Test first-order hypothesis. For first order, T1/2 should be constant, but T1/2 changes from 24 to 12 when A0 doubles. Not constant. First order is ruled out. Step 3. Test second-order hypothesis. For second order, T1/2 is inversely proportional to A0. Check the product T1/2 times A0. At 0.50, 24 times 0.50 equals 12. At 1.00, 12 times 1.00 equals 12. At 2.00, 6 times 2.00 equals 12. The product is constant at 12. Confirming second-order kinetics. Step 4. Calculate K. For second order, T1/2 times A0 equals 1 over K. So K equals 1 over 12, which is 0.0833 per molar per second. Verification. T1/2 equals 1 over 0.0833 times 1.00 gives 12 seconds, matching the experimental data. Answer: the reaction is second order with K equals 0.0833 per molar per second.